Now, a family of open set is a basis of this. If now let me first explain what this theorem says before we now go to the proof. They say that the third definition, a family B, this B, you have this one like this, right? They say of open set. They said it's a basis of this, of the topology, right? If every element in the topology, that is, when you have the topology, let's say these are the elements in the topology, A1, A2, A3, A4. For example, do you understand? If you take every element in this topology, any element you take, are you getting my point? Are you with me? If, let's say for instance A1, this A1 too is another is a set to itself. It has elements inside it. If you take an element in the topology, let's say A1, you now pick a set inside S. Do you understand? That's what this one is saying. For every element in the topology, and you now take, and for every element, let's say you have taken one element now, choosing one element from the topology, and that element, let's say for me now, see I chose A1. Every element in this A1 too, every element in this A1 and in the element you are taking from topology, there exists a what's it called? An element in this basis. The first can call a basis. There is an element in this basis such that S will be inside what? The basis, and it's also it's a subset of the element you are taking in the topology. So now we want to prove. What do we want to prove here? We want to assume that if you have a base, this thing holds. Do you understand? If you have a basis, this thing holds. And we will now also prove from verse since we have if and only if. Do you understand what I'm trying to say?
That is like an element in another set A1.
Yes.
And that A1 is also a subset of
it's an element inside topology. Yes. Do you understand?
How will you form? How is it the X that is the basis? B.
Do you understand? It means that, let me tell you what it is. Every element in this topology, how many elements do we have? A1, A2, A3, A4, right? Now, in each of A1, A2, A3, A4, this is also another set itself. Do you understand? Let's say maybe A1. Let's say maybe A1 is 1, 2, 3. Do you understand? A2 is maybe 2, 3, 4. A3 is 4, 5, 6. And A4, 5, maybe 7, 8. Do you understand what I'm trying to say now? You see that this A1 is also another set. Are you getting my point? So, if I pick one, if I pick A1 first, A1 is an element of the topology, and I pick one is an element of A1, and A1 is inside topology. It means that any element I pick inside here, that element will be inside an element in this basis.
Will be inside an element in this.
Yes, they say family B. This family B, this is the basis we are talking about. This B is actually equal to B1, or this B1 too. Like maybe B1 to B3. Or this B1 too is also a set. It has their own what's called element to inside. Do you understand? Do you get that now? So it means that every element, maybe somebody might decide to choose 5. 5 is an element of A3, and A3 is inside the topology. Do you understand?
The basis belongs to the topological space.
The basis belongs to the topological space.
Yes.
Were you in the first class? That's right. That's part of the reason. That's the reason why. So, but just follow what I'm trying to say. If you take 5, 5 is an element of A3, and A3 is inside the topology, right? See, every element, all this 1, 2, 3, 2, 3, 4, 4, 5, 6. If you pick any of them, any element you pick here, you will find an element here that also has that value. Are you getting my point? That's what that if it happened, then it's a base. Let's say for instance I pick 5 as I'm explaining, right? As I pick 5 here, I'll go and check which element has 5. There must be one of either B1 will have 5 or B2 will have 5 or B3 will have 5. Like before you go through everything here, there must be one of the elements that must have 5. If you go through all of them and there is no element that has 5, then it's not a basis. You understand? Pick any number. Like if you pick all of them, if you pick all of them each, you will find an element inside the basis. Do you understand? That will contain that element. That's what it means. Say for all G in the topology, that is for every element in the topology, and you now take what's it called? You now take an element in that element you're taking. Or let me put it this way: for every set in the topology, you now pick an element from that set. There will be another what's it called? Set in the basis, such that that S will be inside the element in this basis, and this basis will be subset of what you have taken. Do you understand? So now we want to prove. The first thing that let B be a basis. When you say let B be a basis, what does that mean? That means that first definition holds, right? And what's the first definition? That is, you will take an element in the basis and in the topology, you can write the topology as a union of the basis. So now I'm coming. Since this is what I want to prove, I want to prove that for every element in the topology and for every x in G, there is B in Z, so that this one holds. So now let B be a basis, right? I will now say let G be in this one, right? Not only that, and S be in G. Do you get that? If G is in the topology and B is a basis for it, what does that mean? It means that G can be written as a union, isn't it? Of I in I, or Bi, isn't it? Where what? Bi belongs to the basis. That's from the definition of a basis, isn't it? Right? Now, you now say that S is in G. S is in G. What does that mean? S is in G implies that S is inside the union of what one. It means that S is in the union of I in I of Bi. And the way I have explained the first one for you, you know that I explained to you that if S belongs to the union, it means that S is an element of some of these things, isn't it? You know, I was telling you, I gave an instance, an example to you the other day. So I gave an example the other day.
You were making that A1, A2,
being the element of a topology.
An element of the topology.
Yes.
Okay. Now, in this case, can we assume that that G is taking the position of A1?
Yes. Correct. Yes.
And 1, either I pick 1.
Yeah. Is yes. Okay. Good. Very good. Yes. Yes. So now, you know, I told you that if you can remember, I said if A1 is 1, 2, 3, and B and maybe A2 is equal to 2, 3, 4, right? And maybe A3 is equal to what? 3, 5, 7. What is A1 union A2 union A3? What will it be? 1, 2, 3, 4. Isn't it? 5, 7. Isn't it?
Yes.
Now, 2 belong here. 2 belong to A1, isn't it? Union A2, union A3. 2 belong there now, isn't it?
Yes.
That because for 2 to belong in this union, but 2 will be in A1, union A2, union A3. It means that it's either 2 is in A1 or in A2 or in A3 or more. Do you understand? Because if 2 is not in A1 and 2 is not in A2 and 2 is not in A3, it can never appear in their union. Do you understand? Are you getting my point? So this one, they say S is in G and G is equal to union of I and I of BI. It means that since S is in G, it follows that S will be in the union, right, of BI. Do you understand this one I have written now? And what does that mean? If S belongs to the union of BI, it also means that S will belong to some of this BI. Do you understand? Like the way I have explained, if 2 belong to A1, union A2, union A3, it means that 2 will belong to either of A1 or A2 or A3 or more. Do you understand? So it means that S should be in BI. In your note they say BI not. This BI not is just saying, is just like trying to tell you that it's not that S belongs to all of the BIs. Like in this case, 2 is not in A2, isn't it? But 2 is in A1 and A2. Do you understand? So S belongs to BI not. They will not say for some. They will not say for some I not in I. That is, it's not in all the OBI. It's not necessary that it belongs to all the OBI, but it's in some of them. S belongs to BI not for some I not in I. Are you getting my point?
I have one more. That G. Okay. The other time, if I'm relating it with A1, A2, A3.
Yes.
Does it mean A1 if I pick any of them? Since you said A1 and G, A2 and G.
Yes.
Is now a union of all those P1 sets.
Yes. Yes. Yes.
Is there a way you can differentiate?
Like why G is the union of all this one? Because B is a union of G is a union of all this one because B is a basis. That is from the definition of a basis. That is every element in the topology can be written as this. Yes. So do you understand where I am now? So it means that see, it means that S belongs to BI not, isn't it? I've written it before. For some I not in I, right? Yeah. And what does that mean? This BI not is in the basis, isn't it? Yeah. Right? S is a member of BI not, isn't it? Yes. And this BI not, where BI not is an element of what? It's an element of the basis, isn't it? So now S is in BI not, and BI not is fully inside the union, isn't it? Fully inside the union of I in I or BI. Do you understand? Any question? Do you understand? Right? Yes. So I'm done. S is inside S is inside BI. See now, union of all these ones is what? Is G. S is inside BI not and is inside what? G. That's what I want to prove, so that S is inside B. And this B must come from the basis. This BI not is coming from the basis and it's inside G and it's inside G. So I'm done. I'm through. I'm sorry. Yeah, you sure I'm done.
Sorry. That G equals union of BI is a standard.
That G. Yes. That's the definition of a basis. Yes. So I'm done with the what's it called? The right way. It now remain conversely now. Now conversely, I have if and only. If and only you prove to the front and to the back. Now conversely,
and then conversely like vice versa. What's the interpretation of this conversely?
Wait, let me tell you something. They say that let S be a topological space, right? A family B of open set is a basis of top. Listen, if and only if, whenever you have if and only if, it divides the statement into two. This one is like the first part. All this one is general. Let's say no matter the topological space. Leave that one. A family B of open set is a basis of this one. It's like one statement. Do you understand? It's like one statement. P. Do you get that? Are you following? Then I have if and only if. If and only if. This is how they write if and only if. If and only if for all these things. It's like the second one. Q. Do you get that now? So if you now want to prove this thing now, you will first prove P implies Q. Do you understand? You first prove P implies Q. Then you will now do Q implies P. So it is when you are doing Q implies P, they will now be saying conversely. So like the first one I have done now, yes, see what I said. Let this one be a what? Basis. I'm using P, a family P of open set. It's a basis of top. Do you get? I started from P. I want to prove Q. Yeah. Do you understand?
We've moved from P to Q.
Yes. So all the things we have done, we have to move from.
Does it mean we will start reversing?
No. You will take what you have here. Now I want to look at when I'm done. You understand? Do you get that now? Conversely, listen up. Let what G be in topology and S be in G. Do you understand? Let G be in the topology and let S be an element of G. Do you understand? So that and let there exist be in the basis, right? And let there exist this one be in the basis so that, do you understand? I'm starting from Q now. I'm saying that let this thing hold. Do you get what I'm doing now? Let this thing hold. I want to prove that this B is a basis. Do you get? I want to prove that what? See, I've written this all this second thing now. I want to prove that what B is a basis. And how will I be able to prove that B? What am I supposed to show before I will conclude that B is a basis? It means for me to prove that this B is a basis, what I need to show is that every element, this G can be written as a union of elements here. Are you getting my point?
Yes.
I want to prove that P is a basis. It means for me to prove that P is a basis, it means that every element of a topology can be written as this. That's what I want to prove. Do you get that now? Yes. That's what I want to prove. So I'll say, I've assumed all these ones now, right? I said S is inside B. B is coming from this one at B, right? Let me write it as BI. I have my reason for putting I so that the proof can be easy. Do you understand? Where BI is in the basis. Although this BI is just notation, I can still write this one. Now, if I put this one as a set, this is an element of this set, and this one is inside G, right? If I put this one as a set, put it as a set S, right? It become, instead of member, it become subset of BI, right? Inside what? G. I will now take the union of everything. Union of S in G of X of S, right? It's inside union of S in G of BI, right? Inside union of S in G of G. Are you getting it? How do I know?
That is S in G.
That it should be S in G. You will see it now. I want to prove that the G can be written as a union of elements in BI, isn't it? That's what I want to prove, right? So that's why I use union of S in G, because I want to do something. You see why I put it now. Now, union of S in G of S. This one means that, do you know what this one will give me? This one will give me exactly, all these ones like this will give me exactly G. Do you understand? Why it will give me exactly G is that, imagine G. Imagine G is 1, 2, 3, 4, 5. Do you understand? And I say union of S in G of singleton S. That means you are taking the union of every element in G. It will give you G. 1 is in G, Abi. This S in G is representing 1, 2, 3, 4, 5. 1 is in G, right? That means singleton 1 union. You know what this big union means now? Take 2 again. 2 is in G. Singleton 2. Take 3. Take 4. Take 5. Is there any other element in G that I have not written? No. Now, what's the union of one singleton 1 union? What will be the answer? What
is not equal to G? X is 1.
Okay, of all the X is 1.
Do you understand? Everything will give me 1, 2, 3, 4, 5, which is exactly equal to G. Do you understand what I'm saying?
I class.
Do you understand what I'm saying? So all this one is G, and it's inside U of S in G of BI, right? This one, see, union of G of element in G. Everything is still what? G. Do you understand? Now, for a set to be equal to each other, if they say a set A is equal to a set B, what does that mean? It means that A is inside B, isn't it? And B is what? It's inside A. See now.
If they do it, does it mean we have to put a slash under that inside?
Not necessary. If A is inside B and B is inside A, it means they are equal.
That slash is not there.
Which one is last?
For me, it's talking about this. Well, proper and improper subset.
Proper.
Leave that one. Just subset. When you just have to proper, when you have to make proper. So now, see, G is inside this one. Hello. To round up this proof, what do we have? To round up this proof, we have G. So this G is inside what? The union of S in G of BI, right? Now let me write again. Union of S in G of BI is also inside what? G. What does this mean? A is inside B and B is inside A. What does this mean? It means that G equal to what? Right? And since G is taking arbitrary, just let G be in. See, I've written the element of this topology as union of BI, and this BI is coming from B. So that means B is a basis. Therefore, is a basis. That's all. So please write down if you are. So now, solution to that question. You are given X in space PQR, right? And you are given a kind of, should I call it base? But they want us to show that it is actually not a basis. Show that B is not a basis for any topology. How do we show that this is not a basis? Now, number one is that you now have three definitions of basis now. You use the one that suits you. The first definition is all the O elements in the topology can be written as a union of elements in the base, isn't it? But this one, you are not even giving a topology at all, right? that means that one will not be that useful. But that second one, you are not giving any topology there. You just say that the whole set can be written as a union, isn't it, of the elements in the basis. And if you take any two sets from the basis, right, and you pick an element there from their intersection, that there will be another one inside there so that S will be in C. Do you understand what I'm trying to say?
S belongs to C and C is a subset.
The other time we said if it is a topology, one of the elements, let's assume that we are assuming that X is T. X is a topology. Do we have to assume that it's a topology?
Will you have to assume that X is a topology? No. You know, this is space now. If you want to give you a topology, they will give you. If you want to find topology, you will find it. Do you get that? But that's right. We have to show that B is not the basis of any topology. That is, even if we define a topology on this set, it will in this particular that B will not be a basis. Do you understand? So now let's use that one, that second definition. Actually, the second definition, that one, the S satisfies it. You know, S can be written as if you can remember. Also, to that second definition, you see what I'm writing there. If you go to that second definition, you have something like this. But hello, we just have two elements in this basis, isn't it? And if you take the union of the two elements, take the union of this one, PQ, right? Union QR. What do you have? PQR, isn't it? PQR, which is actually equal to S, isn't it? So the first condition is actually satisfied because I can write S as a union of elements in the basis. But the second condition I'm talking about, I was giving them in last class. This is number one. And what the second definition is? It says that if you take B1 and B2 in the basis, isn't it? No, in the basis, right? And you now take S. Then you guys get over class. It's just making noise. Right? If you take an element in their intersection, then after that there were this word a C, thank you, in the basis, such that S will be in what C, and C will be a subset of B1 intersection what? Right? Do you understand? This is if you remember the second definition I gave you on that basis. This is what I gave you. Now, I will now want to use this one on it. Now, let's pick two elements from the basis. These are the two elements we want to pick. Let B1 be equal to PQ, right? And let B2 be equal to what? QR. Are you getting my point? Now, you know we want to pick an element in their intersection. Let's even get their intersection first. B1 intersection B2 will be what? Q. So that means the intersection is even a singleton set. That means it's only Q we can even take. The element we take from here. Right? You know, from here you can see, obviously, Q belongs to their intersection. B1 intersection B2, isn't it? Now, so, you know, I've done this one now. There is this thing, another element in B, such that what? Now, which show me the C that has Q, but it will not be in their intersection.
Now, belongs to that C.
There will not be a subset of the intersection of this one.
You see that is
Just one element. Whether another element, even if you take the same element.
Our X and our Q now.
Yes.
We are looking for C now.
Yes, in this basis.
Why did we call X our Q in this case?
Because the intersection. Right?
A small x.
Yeah. So what do we do? Of course, we can see there does not exist any C in what's it called in the basis such that Q will belong to that C, and C will now be a subset of B1 intersection of B2. There does not exist any of them. Okay? Does. Is the basis. So please let's write. No, when it can ask you in exam, but not this particular exam. This particular example is to say, let this be a topological space, a collection. You know, when I wanted to define a basis, like the first definition of a basis, you know, we also call it a family or a subfamily B inside the topology. That is, the elements inside a basis are open set. The elements also inside the sub-basis are also open set because they are subset of the topology. And every element in the topology are called open set. Do you understand? In fact, there is a collection. This is a notation in the topology of open set, isn't it? That's everything here. They are open set of X is said to be a sub-basis of the topology. If the finite intersection of member of this one form a basis of top. What does that mean? It means that if you take this one will be a sub-basis. Let's say I have let's say I have X. X is maybe A, B, C. Right? Let's say, you know, this is a set. You know, the empty set. We now define a topology on it. Maybe, I don't know, the empty set and the whole set. A, B, and B. This one is not like, I'm not necessarily particular about accuracy, but I just want to illustrate something. You know, this and this together is called a topological space, right? You now have a basis. There will be a basis for this topology, right? There will be a basis for this topology. You now have another to call a sub-basis. Maybe this one is A1, A2, A3, A2. This one will be called a sub-basis of this topological space if the finite intersection, that is, if you take the intersection of all these things you have here, of every element you have here, yes, it will form a basis. Do you understand? That is, if you are taking intersection of all these things here, if you are taking intersection of all these things here, it will form a basis. If you take the finite intersection of this thing here, let's say they are A1, B1, B2, B3, B4, B5, B6. How many elements is in the basis here? 6, right? By the time you take the intersection, like different intersection of this thing, of this basis, you must get B1, B2, B3, B4, B5, B6. Do you understand? You know, if you take any different, you do A1 intersection A1, A1 intersection A2, A1 intersection A3, A2 intersection A3, A1 intersection A2 intersection A3, A2 intersection A3, A3. Do you understand?
Intersection of all those
finite intersection. Do you understand?
I want to hear something. If I do A1 intersection A1, A2 intersection A2, the intersection is what we do.
Yes. if you take the intersection of elements in this place, do you get that? Don't worry, I will example on that. If you take the intersection of everything here, do you understand? Maybe when you take A1 intersection A2, maybe the answer is empty. A2 intersection A3, maybe the answer is another thing.
Write everything.
Yes, write everything together. No, the combination, the collection of all the answers. Yes, the collection of all the answers you get. Put it inside another set. Now check that one with the basis.
To be the same.
Yes, or it will form a basis. Do you get that now? It must form a basis. If not, then this is not a sub-basis. Do you understand? So that's why I say finite intersection of members of this set form a basis for the topology. Do you understand? So now, that's the definition of the sub-basis. So are you getting it? Now, actually there's an example here, but that example is wrong, it's not correct. So, and I don't want to write it. But why I do not want to write it is because there's another example later that will still explain all this thing. That's why I decided to ignore the first one. The first one is wrong. But now, how you use it? No. You can never set a wrong question in the exam. I'm sure that every in that class he would have corrected it. So now let S be not empty and this one be any collection of subsets of S, then this is another definition of the subbasis. Now, this theorem, actually I'm not going to prove this theorem, but you need what it says. You need what it says. Now,
It's not part of what
we actually prove it in class, but it's not necessary. You can omit the proof, but you must know the theorem. Now, let me explain what this means. He said, let S be different from the empty set. Let S be not empty. And let this one, this notation, be any collection of subset of X. Do you understand? If you take subset of X now, no, S is not empty. It will have subset. Yeah. Now, if you take the subset of X, you put it start another set and you call it this epsilon. Now, let us say then this one is a subbasis for some unique topology. This called the topology generated by this. Let me explain what it means to you. Let me give you an instance. Let's say S is 1, 2, 3. Right? Let's say it's what? 1, 2, 3. Now, let me give you the subset of X. You know that every set is a subset of this one. Do you know that? 1 is the subset of this X, 2 is a subset, isn't it? 3 is a subset, right? Now, you see that I put it inside another set. I now call this set epsilon. This thing. Do you understand? Then now say that this one it is a sub-basis for some unique topology. This. That is, if you change this one to a topology, there will be a sub-basis for it. Like if you change this subset, you know all this one are written is a subset, right? If you take the subset that you have called epsilon, right? If you make it a topology, right? You can always find a sub-basis. Do you understand? You can always find a sub-basis for it. So say then this one is a sub-basis for some unique topology. This is now called a topology, called the topology generated by the sub-basis. A sub-basis can generate a topology. Do you understand? So the proof is omitted actually. Omitted. Let S be this, right? And you are given a sub-basis. Then actually you should find unique topological on this generated by this, right? Now, I'm giving a sub-basis to be this, right? To be equal to I have Q, isn't it? I have RS. What do we want to find? Topology, isn't it? Topology for this set. A unique topology for this set. Now, number one thing is that the topology, actually, topology is equal to the union of members of what? Of the basis, isn't it? Do I have a basis here? No. I don't have a basis here, isn't it? Right? Now, but I have a sub-basis. I'll first get a basis from this sub-basis. How am I sure that I'll get a basis? From the definition of a sub-base, what did I say? S is said to be a sub-base of dot. If finite intersection of members of this thing form a basis. Do you understand? Since this is a sub-basis. Do you understand?
Yeah. So that
is a sub-basis. Now, we first find, if you now find finite intersection of this set, the answer we get is a basis. Do you understand? No, this one, that's the space, thank you. That's, yes. Yes. Right?
Actually, you are any small thing the bank will pay, we need it, just tell us.
So now, see, we'll now do finite. See, we'll do. Let me show you how to do finite intersection. We'll first do Q itself. Intersection Q itself. What's the answer? Q. You do RS too. Intersection what? What's the answer? RS too, isn't it? You now do PQR. Intersection what? PQR. What do we have? It's the same PQR, right? Right? Now, yes, intersection of system 2 is there. You will now do now 0 Q intersection RS. What's the answer? Empty. Right?
So we are assuming that S is taking the place of T. It's going to form
the question. You want to form the basis you first before you get it. But in reality, you want to get it. Are you getting it?
Yes.
From the definition of a subbasis. Yes,
I thought we take everything together.
Don't sleep, bro. Don't sleep. Let's continue. Then next, hello. Now, what do I have? Q, intersection, P, Q, I've done RS. P, Q, R. What's the answer, please? It's just Q, right? And it's theorem. Now, there's now remaining this one. RS, intersection, P, Q, R. What's the answer? What's the answer now? R. Right? And if you do the intersection of this empty set, maybe I should write it. U intersection R S intersection P Q R. The answer is empty set. So now, what are the So the basis. So see, all the answer I get is the basis now. Do you see now? All this collection of all this answer without repetition is the basis. I have the empty set, isn't it? I have Q. I have R. Which one again do I have? RS. I have
It generates.
R. Where is S? So you can see that the intersection of all the elements in the sub-basis, like I have told you, form a basis. To now get the topology, yes.
What did you say?
I said that the union of all the elements of this basis now will give the topology. So I think in order not to the best way to do this.
But then when we get is it the page remember from page?
Yes.
We get members for the topology, not for topology.
We get members. Yes. We get the element of the topology, and if you join the whole answer you get, if you put them together, it's a topology, and that's what they want us to find. So union, let's say the empty set.
So the collection of all those intersections and basis.
Yeah, thank you. And the reason is because this is a sub-base. Do you understand? You now do R. Also have the empty set.
The class now,
Right? What if
We have done the two at the same time.
you know intersection?
Yeah.
How will you do the two at the same time? Is the element in the sub-base equal to the element in the base? No, I don't give that.
I think in the basis is X and X being
ẹ má tún gbé ti kíláàsì ẹ má tún gbé àwọn láì kẹ́ẹ̀kì.
X must just always be the topology, not necessarily the base.
Lẹ́yìn bá ti get am ìjà mẹ́fà.
If we take the union of all this one now, union of this one is makes sense. This one, you know what? Then this one there, Q R S P Q R. Someone give me R Q R S RS. Tell me what? QRS. Tell me what? RS. Okay, I can't see.
RS.
Tell me what? PQRS. And this one. Do you know that we are not through like this? Topology we are going to have, of course you can see we have the empty set, isn't it? We have the O set S, we have Q, right?
Yes.
We have R. What do we have? We have QR. We have RS. We have PQR. We have QRS. Right?
Then we have
PQRS. What again do we have that we have not mentioned?
Close curly bracket.
So that's the unique topology that are going to obtain.
So naturally, we will just have to have X in the basis.
Whenever you have empty sets, you should have one X.
Yay!
Anyway, you have no. If you look at it, if any of the union will not give you X, add X. That question is an exercise. They say let X be not empty and take a family of topology, that is T1, T2, T3, T4, T5, many of them. Let's define it. Let's define all those topology on X. Do you understand? Now they show that the intersection of all of them is also a topology on X. No, it's just it's an exercise. So yes, it's an exercise. Yes. It means that if you collect, let me tell you something. When you have a set S, are you getting my point? You can define more than one topology on this X. Do you understand? You can define a topology. The two of them like this is a topological space. You can take another topology different from this T1 and it will still satisfy all those three axioms. It's still a topology. Do you understand? Like you can define. So the point is that if you take as many of them
As topologies.
yes, so that they are topologies. Do you understand? Now, if we take the intersection, see, intersection of all the topology you can define on a non-empty set. Please pay attention. If we take the topology, if we take the intersection of the whole topology, you can define on the set S. The intersection is also a topology.
On X.
On X. So so that we will not hello, let it be equal to that intersection of I in I of Ti. We want to prove that this is a topology. We want to prove that is topology. Right? And now I've defined what a topology is for you before. If you want to know that something is a topology, what do we prove?
By one that empty set and X itself belong to that topology.
Yes.
And then we say let them know. And we have a collection
Thank you very much. Collection of elements of topology. Their union will also belong there, right? And finite interactions will belong there. Now, so if you want to, number one, we have to prove that the empty set and the O set belong here. Do you understand? Now, since all the OTIs, since all the OTIs for all I is a topology or a topologist.
We are topologists.
Right? What does that mean? Since all the OTI for OI are topologies, it means that the empty set and the O set, since they are topology, from the definition of topology, it means that the empty set and the O set are inside all those TI for all what? And if the empty set and the O set is in TI for all of them, it means that what? The empty set and the O set will also be in their intersection. Do you get that? What's the second thing?
Come again, please.
Obvious.
You want to put at the empty set.
Obvious.
You want to put at the empty set and the O set belong to the intersection. Do you get that? And after that, since all these TI, all the OTI, they are topology. You know, there's be a family of topologies. They are all topology. And from the definition of a topology, normally, when you say something is a topology, it means that the empty set and the O set belongs there. Do you understand? So, since all these ones are topology, it means that the empty set and the O set belong to this one. It belongs to all of them. Do you understand?
Yes.
Since it belongs to all of them, that means if you take the intersection, the empty set and the O set will still be there. Do you understand?
Ram record there.
Now,
How about you? What the?
What do you mean?
now let AI so that I B let's use J because we are using I here. Let AJ so that J is in I be a collection. Hello.
The empty set. Here is the X.
Is the O set now?
Definition of topology.
The X is the one that has T, all the TIs.
What is this?
You know that AJ is a member of both, right? No. Don't forget, when you want to put as something as a topology, arbitrary union of elements of that topology belongs to that topology, isn't it? And finite intersection of members of it belongs there. So AJ is this, right? What does that mean? It means that AJ belongs to the intersection of I in I of this. Are you getting it?
Yeah.
Because this is what I call topology. Do you understand?
Now,
So if AJ is a member of this one, if AJ is an element in the intersection, it means that what? It belongs to all of them. It means that AJ is inside.
Inside CI.
CI, thank you.
All I.
All I.
In I.
Do you understand? Yeah. It means that AJ belongs to TI for all I in I, right?
Yeah.
And if AJ now belongs to TI for all I in I, don't forget TIs are what?
Topology.
The family of topology. They can't as well.
So it means
That's
that
the idea is the
In the
union of all
union of
that
all
way.
the
that was
The first thing, it must belong to the intersection and it will also belong to the union. But there is nothing like union here
we are moving to the
we are getting to it. Since they are elements of our topologies, if AJ belongs to TI, they are union too. You know that their union too will belong to TI.
Yes.
Do you agree? Do you agree?
Yes.
Because this one is a topology, it means that arbitrary union is there.
Yes.
Do you understand? All these TI is they are topology now. Because they are topology, what's are the property of a topology? Number one is that what? The empty set and the O set is there. Number two is that arbitrary union of members of the topology is there. So because TI is a topology, it means an AJ is a member of it. It means the arbitrary union of the member will also be in TI. Do you understand?
Yeah.
So if it belongs to TI for all I, that means that it belongs this union will belong to their intersection. You know, if it belongs to everything, that means it will also belong to their intersection. So by so doing, I prove that this one is like arbitrary union is there. It's now remain finite intersection now. To prove for the finite intersection, to prove for the what? To prove for the finite intersection, it's suffice to just prove for A1 and A2. Thank you very much. Let A1 and A2 be a member of what? So we prove that what? A1 intersection A2 you also belong there, isn't it? Now A1 and A2. A1 belong to Tor means that what? It means that A1 is inside the union, intersection of I in I of what? Of the topologies, isn't it?
Yes.
Isn't it? And A2 right? And this one also means that A1, right, is inside for all I in I. Isn't it? A2 belong to this one. It also implies that A2 belong to the intersection. Right? And it also means that A2 belong to if A1, hello, if A1, what is it?
AD belongs to TI. The union of AD also belongs to TI.
This one implies this is happened because TI is a topology. In the first class, I said that from property of a topology, I gave you number 2 properties. Yes.
And its intersection will also belong to
Yes. Thank you. So then, yeah. A1. So from here, I'm here. right? A1 belongs to 2 means that A1 is inside the intersection. Since I said 2 should be equal to the intersection, right? And if A1 is in the intersection, it means that A1 belongs to everything, isn't it? A2 too, the same thing. What I've done for A1, I've done for A2. If A1 is in T1 for all I, and A2 is in Ti for all I, it also means that it follows that. Thank you. It follows that A1 intersection A2 will also belong to Ti for all I in I, because the whole of A1 is in Ti for all of them. The whole of A2 is in Ti for all of them. Their intersection 2 will also be there.
Please, what if I keep A1, I will say A1 belongs to the intersection of T1.
Okay.
And A2 belongs to the intersection of T2.
Yes.
And I will write an account for all I belong to. I will now say A1 intersection of A2 will also belong to the intersection of A1 intersection open bracket intersection of
Why you complicating
any
yourself?
number is
I understand what you are saying. That I don't need to get to this place. I can just say A1 intersection A2 is inside this. Yes. So this.
I was there. I am there. Yeah,
Nobody go pass.
Let's now have a theorem. I write the theorem and I'll just explain. Topology on S containing. Now, what do we? Let me explain what that means. The topology generated by a sub-basis. You have a sub-basis, right? And it's a subset of what? The power set, right? You know, the previous example that has what's called table, that we draw table. You know, you are within a space and a sub-basis. Then they ask you to define to find the topology, isn't it? That the first intersection to get the basis. Before we now do the union of the resulting answers. Okay, to get the topology, right? No. My point is to know that the sub-basis can be used to generate the topology. Yes. So they now say the topology generated by a sub-basis. But that sub-basis is a subset of power set. Do you understand? Is the intersection, that is, let me tell you how they are not trying to say that if the sub-basis is a subset of the power set, that the topology this sub-basis will generate is actually equal to the intersection of what's called some topologies. Is the intersection of all topologies on X. Do you understand? Do you understand?
Is that containing that summation again?
Containing the sub-basis. Do you understand? That is if you take it, you know, when we define the core basis, we say it's a subset of the topology. But now, if the subbasis is a subset of the power set, the topology, let's say the topology this thing generates, the topology this thing generates is equal to tau, right? If you look at this tau very well, it's actually equal to intersection of all the old topology you can define on X.
That's
Containing subbasis.
I need to make it work.
We have a job in job, please. Well, of course.
I'm sorry. Only the one we have now. We have sigma square here.
Sigma square.
Square. Omi Nabala.
I just remember sigma star. So the topology generated by sigma will not be sigma star.
More than one topology on a set or on a space. Do you understand?
Yes.
Now, in this case now, let's say define let S be non-empty. That is, let S be a space. Define topology tau on it. Then you say S comma tau is a topological space, right?
Yes.
It's not. It's possible that I can define another topology on X. Say R. And this S comma R will also be a topological space. Do you understand?
Yes.
No, if R is here, if R is here, that's going to be linear topology. Now, you know this one is a topological space, this one is a topological space. Now, if R, if one of the topology, right, is a subset of the other one, that is, if you look at the two topology defined, one is a subset of the other one, then we'll be saying that this one is coarser to this R. That's the major word we normally use to draw.
If I want to define
Okay, T is coarser to R.
R is coarser to tau. Then say T is
Final.
so it's minor than this one. Beautiful. Do you understand? Like what we have written here. R is smaller than tau, isn't it? The subset. Or R is weaker than tau. Or R is coarser than tau. Or we say tau is larger than R. Or tau is stronger than R. Or tau is finer than R. Do you understand?
How will you know that?